Yes, Nitin sir, please restart.
Okay, sir. Thank you. Right. So, hello everyone. Uh, Welcome to the session where we're actually going to solve the problems of GATE 2023 aerodynamics the problems from the aerospace paper. Let's look at the mark distribution first. So we have around 4 1 mark questions and around four 2 marks questions. Sorry, there's a typo here. It's 4 2 mark questions. So totally the mark tally comes out to be around 12, which is quite substantial when you look at the aerodynamics portions. Right. Let's get on with the problems. So the first problem, a two-dimensional potential flow solution for flow past an airfoil has a streamline pattern as shown in the figure. Which of the following conditions is additionally required to satisfy Kutta condition? So there's a potential flow past an airfoil, and thus the streamline pattern as you see over here. So they're asking which condition is required to satisfy the Kutta condition. So we know that Kutta condition tells us that the flow must be leaving very smooth. So in the figure here, you can see that the flow is not leaving that smooth because your the streamlines are shifted, not at the trailing edge, but have shifted upwards. So the right option here is for an airfoil to develop some kind of lift and to have a smooth flow over it, it needs to have some kind of circulation on top of it. All right. So circulation, if there is a circulation around a closed curve surrounding your airfoil, or there's a circulation over your airfoil, it means that the airfoil has some kind of lift. So we definitely need a circulation of strength gamma and not a source of strength, because circulation is what is actually creating the lift. We know that from potential flow theory that only if you superimpose a circulation over a right circular cylinder, we get some lift out of it, right? And then we also need to see which they have given the option counterclockwise or clockwise. So in aerodynamics, we always take clockwise as positive, but in mathematical sense, clockwise is negative. That's why you see clockwise is gamma less than 0, according to this mathematical sense. But in aerodynamic sense, clockwise is positive for us. And for to get positive lift, that if you want a positive lift over your airfoil, which is what we certainly do want, we need a clockwise circulation over my airfoil, and hence that will basically enable a smooth flow over my entire airfoil. And the right option here is option D. Right. Next problem. Consider the Blush's solution for incompressible laminar flat plate boundary layer. Among the following options, select the correct relationship for the development of momentum thickness with the distance x from the leading edge. So we know that according to boundary layer theory, the Blush's solution for momentum thickness is basically something like delta by x equals to some constant divided by root of Reynolds number with respect to the location along the flat plate. And this constant is different for, let's say, a displacement thickness has this value of 5 point something. Momentum thickness has a value, the constant is around 0.3 or something like that. So it's some constant, but the relationship looks something like this. All right. So now if I take this x to the other side, it would look something like this. And if I open up my Reynolds number expression, my Reynolds number is nothing but rho v x by mu, and in the numerator you have another x. So this x for half and this x would cancel, and then this would be nothing but x power half. So your theta is basically directly proportional to or half square root of x, right? So option B is the right answer over here. An easy problem. Next problem. In a two-dimensional potential flow, the doublet is a limit of superposition of. So basically, they're asking us how is a doublet formed. So we know that from potential flow theory, if you bring a source and sink of some strength, let's say gamma and minus gamma, very, very close to each other. That is, the distance between them is pretty much uh, zero, but their strengths are infinitely high, and that basically produces a doublet. So, and from the given options, we have uniform stream and a source and a sink of equal strength, which is basically our right option. We have a source and a sink of equal strength, and that to infinite strength coming together in a very, very short distance. Right? Let's look at this problem. Airplane A and airplane B are cruising at altitudes 2 kilometers and 4 kilometers. So you have airplane A, and then you have airplane B. This is cruising at the altitude of 2 kilometers, and this is at 4 kilometers, right? The free stream density and static pressure at altitude 2 kilometers are 1.01 and 79.50. So density at altitude A is nothing but density at the altitude where my airplane A is flying is 1.01 kg per meter cube. And the static pressure over there is 79.5 kilopascal. And at altitude 4 kilometers, the density is 0.82 kg per meter cube. Kg per meter cube. Right? And there's a static pressure of 61.7 kilopascals. The differential pressure reading from the pitot static tube is 3 kilopascal for both airplanes. So the pitot static tube basically measures your dynamic pressure, right? So the dynamic pressure QA in this case is 3 kilopascals, and even in the other case as well, that is this in the case of airplane B is also 3 kilopascals, right? So assuming incompressible flow, the ratio of cruise speeds of airplane A and airplane B are. So they want us to find what is VA divided by VB, right? So we know that your dynamic pressure is nothing but half density into velocity square, right? Which is basically 3 kilopascals in both cases. So let's use that. So QA is nothing but half rho A into VA square, and so 3 kilo QA and then VA is nothing but square root of 2 QA by rho A. And because we know what is QA, we know what is rho A as well. Similarly, QB is nothing but half rho B VB square. Right? So now VB would be nothing but square root of 2 QB by rho B. If I were to take the ratio VA by VB, this would be nothing but square root of your QA QB, QA, maybe I'll just write it down. So 2 QA by rho A divided by 2 QB by rho B. Right? So your Q and QB both are same, which we already know. So it's ultimately the square root of the ratio of rho B by rho A and rho B is from the question 0.82, rho A is 1.01. Right? So this will turn out to be a value of around 0.9 for that matter. The ratio of the cruise speeds are VA, that is VA by VB is nothing but 0.9. Right? Easy problem. Look at this problem. The operating characteristic of a pump were measured to be Cp equals A phi square, where power coefficient Cp is power divided by rho omega cube T power phi. Phi is a flow coefficient. A is a constant. Okay, so phi is definitely a non-dimensional number because Cp is also non-dimensional, right? Because Cp is nothing but the power non-dimensionalized with some quantity. T is a length scale, omega is a rotation rate, rho is the fluid density, and P is the power required. All right. The flow coefficient is a dimensionless volume flow rate scaled with omega and T. So what they're saying is phi is nothing but like the volumetric flow rate. Let me call it as V dot, and that divided by that is being scaled with respect to omega and D, and raised to some power, which we need to figure out. All right. Assuming that the flow rate remains the same, so they're saying that the flow rate remains the same if the rotation rate is increased to 1.25, the power changes to alpha P. So what they're saying is that initially we had a rotation rate of omega, right? Then the rotation rate changed to 1.25 omega, right? But though the rotation rate changed, what happened was that my volumetric flow rate did not change, all right? So in this scenario, what happened is that since you're increasing the rotation rate for the same flow rate, what will happen is that your required power, the power required to run your pump is basically going to be increased. So from P, it increased to alpha P. Now they're asking us, what is this alpha value, right? So let's go ahead and then try to find this out. So first, let's find out what is a scaling relationship for phi, all right? We know that phi is volumetric flow rate. So volumetric flow rate has a dimension meter cube per second, right? So which is nothing but L3 T minus 1, all right? So we are scaling this volumetric flow rate, which is L3 by T power minus 1 with respect to omega, which is nothing but you can consider it to be per seconds, T power minus 1, and because the rotation rate. All right, so it will be like an angular velocity, which is radians per second. Hence, its units will be T power minus 1. And then you have D, which is length scale L. So you have T power minus 1 and L in the denominator. So you need and this, so the dimensions of omega raised to A, dimensions of D raised to B. All right. So we know that if A is equals 1, they both will cancel out, which is exactly what we want, right? If A equals 1. And if my B equals 3, then these both will cancel out. Hence, that tells me my scaling relationship of phi looks something like this. The volumetric flow rate divided by omega times d cube. Right? So this is basically the flow coefficient relation from dimensional analysis. All right. Now, keeping the volumetric flow rate the same, they have basically increased your omega. So initially, the phi value was v dot by omega d cube. Now, in the new scenario, let me call this as phi prime. My new volumetric flow, my flow coefficient is nothing but 1.25 omega times d cube. So this would be my new flow rate, flow coefficient. How is the flow coefficient related to Cp? It is A times phi square. So initially the Cp has a value A times phi square, which is nothing but A times volumetric flow rate square divided by omega square into d power 6, right? Then with the change conditions, so your Cp, let me call it as Cp prime, is nothing but A times phi prime square, right? And this is nothing but V dot square divided by 1.25 omega square. Now, because in this new case, your omega is changed to 1.25 omega. This is d power 6 again. Now we need to rewrite. So the idea is basically to compare the powers, right, in both the scenario. So Cp is related to power as power divided by rho omega cube d power 5. So omega cube d power 5. Right. So let me replace Cp with the equations for power. So your Cp prime will be nothing but P prime divided by rho into 1.25 omega whole cube d power 5. So let me replace each of them. So P by rho omega cube d power 5 equals A into volumetric flow rate square divided by omega square d power 6. Right.
A little louder, please.
Oh, okay, sorry. So in the Cp prime, it'll be P prime divided by rho into 1.25 omega whole cube into d power 5, and that is equal to A into, again, volumetric flow rate square divided by 1.25 omega whole square and d power 6. Right. So let's take, we have these two equations. The idea is basically to compare the power, right? So we need to do equation 1 divided by equation 2. So when you do equation 1 divided by 2, your rho gets cancelled out, your d power 5 gets cancelled out, your omega cube gets cancelled out, your A gets cancelled out, your V square gets cancelled out, the omega square here gets cancelled out, your d power 6 also gets cancelled out. So what you're left with is, let me write that in a new page, it will be P divided by P prime divided by 1.25 cube, that is equal to 1 divided by 1 by 1.25 square. So 1.25 square and 1.25 cube, they get cancelled and it's only 1.25. So I can take 1.25 to the numerator. So, and then rearrange this equation. And that basically gives me P prime equals 1.25 times P. So they've told you the new power is nothing but alpha times P. In this case, the alpha is nothing but 1.25. It's just a lengthy problem, but still quite straightforward. Let's look at this problem. A thin cambered airfoil has a lift coefficient CL equals 0 at angle of attack of minus 1.1. So the zero lift angle of attack for this cambered airfoil is nothing but minus 1.1 degrees, right? Assume that stalling occurs with much larger alpha, the CL at alpha equals 4. So they want us to figure out what is the CL at an angle of attack of 4 degrees. And we know it's a thin cambered airfoil. So according to thin airfoil theory, from symmetric to cambered airfoil, the lift curve slope does not change. It remains as 2 pi per radian. The only thing that changes is the presence of zero lift angle of attack. Hence, the CL for this airfoil is nothing but A into alpha minus alpha L equals 0. The thin airfoil, so I can basically take 2 pi. Assume that 2 pi would be my lift curve slope. So my A is 2 pi. My alpha is nothing but 4 degrees, and negative minus of alpha L equals 0. So this would be plus 1.1. And I need to convert this to radians. So I need to multiply it by pi by 180. Right? So this is my CL. So if you calculate this, your CL will turn out to be a value of 0.559. Very, very simple problem. Might appear a bit complicated, but eventually, it's a very, very simple problem. Right. Let's look at this problem. In a potential flow, a uniform stream of strength U directed along the x-axis and 4 line sources of strength pi by 2 minus pi by 3, pi by 4 minus 5 placed along the x-axis at x equals 0, 1, 2, 3 respectively. So what they're saying is that you have a scenario in which you're keeping multiple line sources of various strengths like pi by 2, and there is minus pi by 3, and then you have pi by 4, and then minus pi by 5. Right? And they're kept equidistant from each other. So this is at x equals 0, this at x equals 1, then this is 2, and this is 3, and then you have something at x equals 4 as well, which we need to figure out. The strength of an additional line source to be placed at x equals 4 such that the closed streamlines encircle all 5 sources. So we need to figure out what is the strength of a source that should be placed over here so that when the free stream is hitting this entire ensemble of the entire assembly of these sources, it'll form like a closed streamline, that it won't be an open-ended kind of a stagnation streamline. It'll have a closed stagnation streamline like Rankine full body, right? Rankine full body. So that's basically the question. So here, it might look very complicated, but the only thing that, the trick to this question is that you have basically you need to compare this, or try to get a link between this question and the Rankine full body kind of a question. So let me just redraw this in a new page and explain how do we do this. So you have pi by 2, and then you have minus pi by 3, and then you have pi by 4, then you have pi by let's see, minus pi by 3, by 3, then you have pi by 4, and you have minus pi by 5, and then you need a new guy over here. All right. So and then there is free stream which is coming at the velocity of u. All right. So imagine some point in space. Imagine your origin is at this location. All right. If I were to write the streamline equation, the equation of streamlines for this kind of flow field. So if I take some random point r comma theta uh, in this plane, in this polar plane, so it would look something like this, right? So I'm just joining all these lines so that I can figure out, you know. So let's say, since this is the line joining the origin and the point of interest, so this would be nothing but theta. This would be, a line joining this source and the point of interest. Let me call this angle as theta 1, and this angle that is formed as theta 2, and this angle as theta. Oh, okay. This angle would be theta 3. The reason why we're not taking as theta is because theta is usually from the origin to the point of interest. So these are not from exactly from the origin, right? These are from different points which are shifted from the origin, right? So, and this let me call as theta 4, right? And now if I were to write the equation of streamline for this psi, so firstly you'll have the contribution v infinity r sine theta, which we know from Rankine full body, which we know from the potential flow equation for a uniform flow. Then you have the contribution from sources. So let's take this source first. This is so the streamline equation for a source is given by kappa by 2 pi into theta, where theta is nothing but the angle between the line joining the source and the point of interest. So here the kappa value is pi by 2. So let me use the value of kappa. Pi by 2 divided by 2 pi into theta. And then you take this is minus pi by 3 by 2 pi into theta 1. Then you have plus pi by 4 into 2 pi into theta 2. Then you have minus pi by 5 into 2 pi into theta 3. And then lastly our unknown gamma, kappa by 2, kappa by 2 pi into theta 4, right? Now here you need to make a parallel between the Rankine full body and this scenario. So in Rankine full body, we all knew that we had the stagnation streamline had psi equals 0, right? The stagnation streamline had an equation of psi equals 0. And you basically had a stagnation point, at theta equals 0 and theta equals pi, all right? So which means that if I set my theta, which if I go in my 180-degree direction or phi direction, there is a stagnation point over here, and at some distance r from the center, I'm going to meet that particular point. And we know that stagnation streamline will basically pass, the stagnation point will basically pass to stagnation streamline, making psi equals 0. All right. And this is basically the parallel that we are drawing from Rankine half body, because they are very, very similar scenarios, right? That in Rankine full body, you have a source and strength of equal strength, making a closed streamline. Here, the idea is to create a similar scenario. That is, you want the resultant of all these and plus some additional source that we're keeping here to create a closed body. So we're just trying to draw this parallel. All right. So I'm going to see whether I can find my, if I go my theta equals pi direction. So which means that my sine theta becomes sine pi, and all these theta like theta, theta 1, theta 2, theta 3, theta 4, all these would become, would basically be pi, right? Because though let's say if I take some point, my stagnation point over here, the angle extended from my all these sources to this point would be nothing but 180 degrees, right? If you take any source, the angle theta, theta 1, theta 2, theta 3, theta 4, everything would be pi radians. right? So let me see. So I'm looking for my stagnation point, which passes to the stagnation streamline, hence my psi equals 0. My uv infinity r sine theta. So my sine pi would basically be 0. Then I have pi by 2 pi times pi. So let me cancel out these two pi's, and then theta equals pi. So this would be pi by 4, right? And here, if I take theta equals pi, this pi cancel. This is nothing but pi by 6. And here pi cancel. This would be, and if theta 2 equals pi, then this would be pi by 8. And here pi cancel. Theta 3 equals pi. This would be minus pi by 10. Right? And then lastly, kappa by 2 pi into pi. So I cancel out these two pi's. All right, and then if I calculate all these and then find what is my kappa value, it would turn out to be around minus 0.8. All right, this should be the value of my source of strength at this location, such that this kind of an assembly of sources will resemble to that of a Rankine full body and create closed streamlines. So this question might seem complicated at first, but the prior knowledge of a Rankine half body, like your stagnation streamline is cycle 0, then you have a stagnation point, because we are basically trying to get this assembly very similar to that of a Rankine half body. So what should be this value of kappa that would make this similar to the Rankine half body, Rankine full body, sorry. That's basically how we do this problem. And then the source of the strength of the source at this point would have to be minus 0.68 for this to form closed streamlines and resemble that of a Rankine full body. Right. Look at this problem. Entropy is defined as the square of magnitude of vorticity for a three-dimensional flow field, and the velocity field is given over here. You have your u, v, w. So this is u, this is v, this is w. And the entropy, they want entropy at the location 1, 1, 1, 1. So first, entropy is nothing but square of magnitude of vorticity. So let's find the vorticity. Vorticity, all of you know, it's nothing but del cross v. You take a cross product of the del operator with the velocity. And if I do that, if I were to find the cross product, I would do it in this way. I, j, k, dou by dou x, dou by dou y, and dou by dou z. And you have u, v, and w. The omega vector would look something like this. It'll be I cap dou w by dou y minus dou v by dou z minus j cap to dou w by dou x minus dou u by dou z then k cap of dou v by dou x minus dou u by dou y. The only thing is that you need to put these expressions for u, v, w, n. Right. So let's go ahead and do that. So your omega is nothing but I cap your dou w by dou y, that is this term, which is the first term I'm looking for, is minus 0.7x. If I differentiate with respect to y, I get this minus 0.7x. Let me write that down here, minus 0.7x. Right. Next term is dou v by dou z. So if I take v, try to differentiate with respect to z, it's 0, right? Because v is not a function of z. So this is 0. I have minus j dou w by dou x. So if I differentiate w with respect to x, I get minus 0.7 y. Right? And then minus dou u by dou z. If I differentiate u with respect to z, I get plus 2.5. Finally, have k cap dou v by dou x. If I differentiate v with respect to x, I get 1.5 minus dou u by dou y. Dou u by dou y is nothing but minus 1.5. So negative. Right. So you do this, and you need the entropy at x equals 1, y equals 1, and z equals 1. Right. So you substitute all those coordinates here, and finally you'll get your omega as 0.7 I as 1.8 j and plus 3 k. Okay. This is the omega. So now entropy is nothing but magnitude of omega square of it, but 0.7 square plus 1.8 square plus 3 square. This entropy can be given as the value would come out to be around 12.7. That's how you would solve this problem, right? So with that, yeah, we reached the end of all the questions. I hope this has given you a sense of how we typically tackle the problem. So there are problems which might seem very lengthy, but the idea is that in GATE, they would never ask you problems that you would have extensive derivations or things like that. So always the trick is to, if you're spending a lot of time on a question, then you're probably doing it wrong. So with that in mind, all the best to everyone.